Hello friends of Rock the JVM, this is Daniel, and in this video I'm going to teach you how to read and interpret Spark DAGs. So in this video I'm going to give a gentle introduction to how Spark prepares computations in the form of a Directed Acyclic Graph, or DAG for short. This is foundational for performance analysis and optimization. So this is an essential skill before you can optimize any of your Spark jobs. Now, this video is for the Spark programmer who has some basic fundamentals about Spark, for example, how to create a data frame and how to do basic selects or joins, but this video is especially suited for you if you have not dived into how Spark works behind the scenes yet. Now, as a recommendation, as always, I will recommend that you code alongside me in a Spark shell, as I will be using it in this video, and attached to this video you will find some links on how to download and install Spark on your computer as well, and whenever you need to refer back to DAGs, just return to this video. This video is also available in written form at rockthejvm.com/blog. Alright, now the code that I will be writing is inside a Spark shell with version 3.0, which you can find for download in the link attached to this video. The default choices in the drop-down selectors over that page at sparkapache.org will give you a precompiled Spark distribution, and it's very easy to install. Okay, now, you're surely aware that Spark has this very lazy execution model in the sense that you write transformations on your data frames, which are the distributed data structures that we operate with. And these transformations are not actually run until you call an action. So when you write transformations, Spark will automatically build up a dependency graph of your data frames, which will actually end up executing when you call an action. Let me give you an example. So let me define a val, let's call this simple numbers, as spark.range 1 to 1 million, for example. So when you write something like this, Spark will create a data set of long, which has the field ID of type bigint, that is a long. Now, let's create a derived data set. So I will write a val, let's call this times 5, as simple numbers dot select expra, which is one of the powerful selectors in Spark. So I'm going to use ID times 5 as ID. So that is under a string. So ID is the column of this data set, and I'm going to multiply that column times 5, and I'm going to rename it to the same ID. So when you write something like this, Spark will create a data frame with the column ID of type long. However, the contents of this data frame are not actually evaluated. Notice that this command was executed almost immediately, but Spark could not have computed 5 million computations in a fraction of a second until we call an action. For example, times 5 dot show. If you call the show method, that will be an action. And if you trigger this computation, notice that it takes a second or two before the data frame actually shows up in this console. Now, whenever you call an action, that will trigger a Spark job. And if you open a browser tab and navigate to localhost 4040, which is the usual address where you will find the local Spark shell that you're writing code into, which happens to be my shell as well, you will have a table with all the completed jobs over here at the Spark UI. And if you click on Show at Console 26, you will see this very interesting diagram over here with these blue boxes. This is called the DAG, the Directed Acyclic Graph. Alright, this is a visual description of all the steps that Spark will need to perform in order to complete your computation. This particular DAG has two steps. One that is called whole stage code gen, which is what happens when you run computations on data frames and generates Java code to build underlying RDDs, the fundamental distributed data sources that Spark natively understands. Then we have the second step called map partitions internal. This runs a serial computation over each of the previous RDD's partitions. In our case, multiplying each element by 5 because that is what we wrote here in this string. We multiplied each element by 5, and this is a map partitions, meaning that every single partition is traversed in order and every element is multiplied by 5. Now, every job that you write will have a DAG such as this, and usually they're more complicated than this, so this is very, very simple. Let's go over some more examples of additional jobs, and let's inspect their DAGs. So I'm going to define, let's call this more numbers as spark.range, and I'm going to define another range, 1 to 1 million in steps of 2. So we have another data set of long, and I'm going to repartition this data set. I'm going to say val split 7 as more numbers dot repartition 7. So I'm splitting this data set into 7 partitions. Now, notice that this data set has been created, so to speak, immediately, but its contents have not been evaluated until I call an action. So let's call another action like split 7 dot take 2, and then for each print line, something like that. So notice that it takes a couple of seconds, and if we get back to the Spark UI, we notice another job here in the table. So the first job is the most recent, so I'm going to use the take. The take is the actual action that's being run. So notice that this DAG is a little more complicated. It has 2 stages over here. So same operation first, the whole stage codegen, but the next operation is an exchange, which is another name for a shuffle. You're probably aware, a shuffle is an operation in which data is exchanged in between all the executors in the cluster. Exchanged means shuffled. The more massive your data in your cluster is, the more expensive this shuffle will be, because sending data over in between executors will take a lot of time. So for performance reasons, it's best to keep shuffles to a minimum. So whenever you see exchange here in your DAGs, that means a shuffle. So a performance tip, whenever you see exchange in a DAG, that is a performance bottleneck. Now, also notice that after this shuffle, we have the next steps of the DAG are another column here in stage number 2. It's like another vertical sequence over here. This is called a stage. So we have stage 1 and stage 2. After every single exchange, there will follow another stage. So an exchange, a shuffle, means that it's an operation that happens in between stages. So this is how Spark decomposes a job into stages. It splits them where it has exchange points, exchange operations, and delimits stages from there. So we have stage 1, which prepares the data set that we wrote over here, the Spark range, and then the exchange repartitioned that into 7 partitions. All right, so I hope that makes sense. Let's do one more, and this time let's make it complex. So I'm going to define, let's call this ds1 as spark.range 1 to 1 million or 10 million or something like that. Let's call this ds2 as another spark.range. Let's call this ds2 spark.range 1 to 1 million in steps of 2. Cool. Now I'm going to repartition each data set. So I'm going to say val ds3 as ds1 repartition 7. Then I'm going to repartition the other guy as well. So I'm going to say ds2 as spark, actually val ds4 as ds2 repartition. And let's pick a number that's different, for example, 9. So I have 2 data sets, and each is repartitioned to 7 and 9 partitions respectively. Now, let me do a complex operation on both of them, but not until I do a map side operation on one of them. So I'm going to say, let's call this ds5 as, and I'm going to process this ds3 with a very simple operation like we saw earlier. So I'm going to say ds3.selectExpr, and I'm going to do the same thing, id times 5 as id. So I have ds5 here, which derives from ds3, which derives from ds1. And we have ds4, which derives from ds2. Now, let me join these together. So I'm going to say val joined as ds5 join with ds4 and under the column id. So this performs an inner join between ds5 and ds4. And after that, I'm going to do an aggregation on this joined data frame. So I'm going to do, let's call this sum as joined select expr, and I'm going to use sum of the column id. So I'm doing an aggregation on this joint data frame. So sum will be a data frame containing a single row, which is the sum of all the values in the joint data frame. So I'm going to call an action now. So I'm going to say sum.show. This will take a couple of seconds because we have quite big data sets. So we have 2 million data sets, 2 million rows actually, and we have the sum of all the elements that are common in between DS5 and DS4. Good, now let's take a look at the Spark UI and let's see what we got. So notice that in this job, although we kicked a single action that we called show here, Spark actually was smart enough to trigger 2 individual jobs. So we have job number 2 over here and job number 3. Let's take a look at the individual jobs. So look at the job number 2 over here and look at the DAG, meaning we have a whole stage code gen and an exchange, which is equivalent to the, what do we got here? We have DS2 and then DS4, which is DS2 repartition 9. So the DAG over here that I have in stage 3 and stage 4 that I have here on my screen are the generation of the data set that I called DS2 and then repartition that into 9 partitions. How did I tell that? Well, I take a look at the tasks column over here in the table below, and we notice that we have 9 tasks in stage number 4, which is the last stage over here. And because I see 9 here, I know that Spark does a single task per partition. And because we have 9 tasks, it means that this data set has 9 partitions. And the data set that I forcefully repartitioned into 9 is this DS4 that I wrote here on screen. So this is how I know that this details for job 2 is actually collecting all the contents of DS4 in memory. And Spark actually collects that into memory because 1 million elements is actually very, very small. It's actually a couple of megabytes. And because of that, the joint expression over here will simply need to collect the values here in this dataset 4, in this DS4 in memory, and then broadcast it to all executors where the DS5 is present and just join that in memory instead of joining in between two separate data frames. So Spark actually collects DS4 into memory and then joins that to DS5. It is a decision that Spark has actually decided on its own based on the number of elements in the dataset, which in our case is not too small. It's just 1 million elements. So this is what the job number 2 is doing. It collects the DS4 in memory after repartitioning it into 9 partitions. So I hope that makes sense. Let's get back to the Spark UI and let's investigate job that I have here with the ID 3, which calls the final show in the console. Now, notice that this DAG is now a little more complicated. We have 3 stages. We have stage number 5, stage number 6, and stage number 7. As a Spark application proceeds, stages are individually numbered in incrementing order. So that is why this job starts with stage number 5, because that is the next number that has not been taken. Good, so let's see what the steps of this computation are actually doing. So we have stage number 5, which has the same pattern, whole stage cogen and an exchange. This is corresponding to computation of the DS1 dataset and then repartitioning it into 7 partitions. Because I take a look at here into the tasks table and I notice that the tasks are 7 in number. That means we have 7 partitions. Now, after the exchange, we have another whole stage cogen and another exchange. This exchange is due to the join that I have over here when I compute the joint dataset. Whenever you need to do a join, Spark will need to make sure that all the keys of the same value are on the same executor. So the join will need to perform another shuffle. So bear in mind when you do joins in your own computations because they incur a shuffle. After the shuffle has been performed, in stage number 7, which is the last stage, we have whole stage cogen and map partitions internal, meaning that the join is actually performed in memory with the DS4 dataset that I explained is computed in memory in the previous job. So this is what this DAG is actually doing. It is a visual description of the computation that Spark will perform before the action is actually being called. All right, so Spark knows all of this. All these dependencies are known in advance. Let me give another example, and let me give you probably the biggest DAG in this video. So I'm going to redefine all these data frames, but instead I'm going to rank up the number. So I'm going to use 100 million elements instead of 1 million, just to make you aware of the fact that Spark will actually make different decisions based on the size of the data. So I'm joining right now 2 data sets with 100 million elements and 50 million elements each respectively. So I'm going to rewrite the same computations. So I'm going to redefine DS1, DS2, DS3, and DS4 with the exact same transformations, and then I'm going to redefine DS5, and then I'm going to redefine the joined dataset, and then I'm going to redefine the sum, and then I'm going to call the action again. So sum.show. All right, now notice that Spark is doing a lot more computation in the back end now. So we're doing 100 million elements, and this might actually take a while. So notice that it's doing stage 8 and stage 9 in parallel. And if I refresh the Spark UI, you will notice that we have an ongoing job here at console 26, and my laptop is probably going to take off. But what I want you to take away from this video is the actual DAG of this job that I identified with number 4. So let's take a look at all these stages. So notice that we have stage 8, stage 9 that are absolutely independent. They're not dependent on one another because these data frames DS1, DS3, and DS2, DS4 can be computed in parallel. And this is what's happening here. So we have stage number 8 with an exchange, which then goes to stage 11 with an exchange. So look at the lines over here. Stage number 8 and stage number 11. And if we take a look at these stages at the bottom, we have stage number 11 due to perform with 9 tasks. So the stage number 11, and my laptop is taking off, stage number 11 has 9 tasks, meaning that it's processing in 9 partitions. 9 partitions is corresponding to the dataset DS4. So stage number 8 and stage number 11 are corresponding to the datasets DS1 and DS4 respectively. And in the same fashion, stage number 9 and stage number 10 are corresponding to the datasets DS1 and DS3 respectively. So look at that. So we have stage number 9, which does the exact same operations, and then we have another whole stage cogen in between. Now, what is that? If you click on one of these stages, you will see actually the details of this stage. So you will actually see the implementations of the RDDs, the distributed data sets, the distributed data structures that Spark actually understands inside this stage. So we have this whole stage cogen, which has a correspondent with a map partitions RDD. A map partitions RDD over here means that a map operation is being performed in parallel on this RDD. And this is corresponding to the select expro where we multiplied each element by 5. So this is what this intermediate step is doing. This is in the same stage because selects such as this one, select expra, non-aggregation selects, can be performed in parallel on the same data frame. So this does not require an exchange. Now, let me get back to the job. And finally, after we've computed DS4 and DS5 after stage 10, we need to prepare them for a join. So the joined data frame that I have here in my console with the DS5 joined DS4 under the column ID is being performed in this massive stage number 12. And you probably can take a guess of which step is actually being performed for the join, which is the exact column over here, the zipped partitions RDD2 that you have over here in the middle. So stage number 2 is performing the actual join. And after it's performed the join, we have another exchange because in stage 13, we perform the aggregation, the sum. And in order to perform a sum, Spark will need to bring all the entries of the data frame into the same executor so that it can perform a computation for a single value. So this is what this stage 13 is actually doing. So I hope this makes sense at least a little bit. If I talked a little bit too fast, make sure you rewind this video and understand each step that I explained here in this massive DAG. This is actually pretty complicated if you've never seen DAGs before, but as you become more experienced with Spark, this will become second nature, reading and interpreting DAGs. All right, this seems tedious, but in practice, this skill of reading and interpreting DAGs is actually invaluable for performance analysis. So you might notice that in this last example, we're doing quite a bit of shuffle. So you notice exchanges here all the time. With time, you will learn to quickly identify which transformations in your code are going to cause a lot of shuffling and thus performance issues so that you can actually mitigate them. All right, so I hope this was useful. I'm Daniel, and you can find this article at rockthejvm.com/blog in written form, and you can follow me on Twitter and LinkedIn with the links in the description attached to this video. Now, I'm dying for feedback, so please leave yours in the comments, and if you like this video, go ahead and subscribe because more videos like this will be coming soon. Until next time, thank you for watching.